Dear Mr. Burns, the meltdown at the plant was Lenny's fault. He ate all the donuts, and I need them to keep my diabetes level high. Anyway.
Hi, Dad. Today was my last day of school, and only 3 more days until the science camp.
I wonder where the plutonium leaked to.
Dad, your computer is on fire.
Oh!
You blocked the fan with your beer.
Beer.
There is no airflow going into your computer, which means you've reduced the convection heat transfer, and the Newton number is decreasing.
Lisa, I'm not moving my beer. You have to go get a better computer.
I know exactly who to ask.
Oh, hi, Lisa. How can I help you?
I was trying to find a better way to cool down the computer system. I knew by increasing the amount of convection, the Newton number increases, and the heat transfer coefficient increases, which means it provides a better cooling system.
You're right, Lisa. We want to increase the overall heat transfer coefficient. Let's go over the basics behind transfer regimes.
We want fluids to either flow over the processor or hit the computer processor directly, both of which produce a boundary layer, as you can see here. This means that close to the processor, the fluid flow is slower than when we put it in, and the shape and behavior of this layer changes with geometry. We should start with the continuity of mass, momentum, and energy equations. Here they are in cylindrical coordinates and steady state. One way to solve the PDE is applying a similarity solution. Different geometries have different solutions. Since this is an axisymmetric jet, I know it's a special case of the Faulkner-Scan similarity solution. After applying the similarity into the energy equation, I would get the heat distribution from the Faulkner-Scan equations and then solve for Newton number. As you can see, it's approximately independent of radius, which means the thermal boundary layer is of uniform thickness. As you can see, the stagnation Newton number depends approximately on Prandtl number.
No, I can't see.
Oh, it's right in the theta prime function. So the stagnation Newton number is a function of both jet Reynolds number and free stream velocity gradient.
So, what does this mean?
It means you can increase the effect of cooling by paying attention to the Newton number, the Reynolds number, and it's the Prandtl number. Why? Alright. If you find the way to relate these parameters, you can improve the cooling system. Here are some books to get you started.
Thank you, Professor Frink.
Hi. This is a real problem. There's too many computers catching fire. I wonder what would happen if I used liquid instead of gases. Liquids are more viscous, so higher Prandtl number, and I can also take advantage of the phase change latent heat. I should choose a liquid with high thermal conductivity and density, but low viscosity, and then put in a strong pump to keep the fluid velocity high, keep the Reynolds number high. Hi. Then what can I do about optimizing the heat flow? The Newton number is highest in the stagnation region. Let's make everything the stagnation region. How about parallel stagnation flows? I can increase the diameter of each flow to further increase the Reynolds number, which is all part of the Newton number, and better heat transfer coefficient. Hi. How about 16 jets per chip, diameter of 0.3 millimeters, and use pump power of 0.6 watts per chip. I'm going to bring this to Mr. Burns, the richest man in town. I didn't make my millions installing Convective jet who's a what's it into computers. Get out! Smithers, release the hounds.